Okay, I think we should go ahead and get started, even though more people are still joining. Let me first of all welcome everybody to the new webinar series organized by the Black Hole PIRE grant. The new webinar series is going to focus on Sagittarius A star, the black hole at the center of our own galaxy, which we know and love very much. And our first talk today is going to be by Daryl Haggard, a deep look into the webinar series is a deep look into the black hole in the center of the Milky Way. And we're going to get started today with Daryl Haggard. Let me give you a little bit more information about our webinar series before we go on to the talk. All the previous webinars are available on YouTube, the Black Hole PIRE Science channel, and the link is in the chat, so you can access all of our previous series on black holes and observational techniques and theory there. In this new series, our next speakers are going to be Sarah Issaoun and Andrea Ghez, and the last in the series is going to be a talk by myself. And we are really excited to bring this Sagittarius A star experience to you. Today's webinar is titled Entering an Era of Black Hole Discovery. And who better to talk about this than our speaker, Daryl Haggard, who is a tour de force in understanding both different ways of studying black holes and in particular, the black hole at the center of our galaxy itself. Daryl is an assistant professor of physics at McGill University. She's an observational astronomer and received her PhD at the University of Washington in Seattle. She has a very interesting career path, but I'm not going to get into that. She and her group study Sagittarius A star, our supermassive black hole, and she uses radio, submillimeter, near-infrared, and last but not least, X-ray telescopes to study Sag A star, a truly multi-wavelength and tour de force campaign of understanding black holes. And she looks at the Sag A star's exotic environment where strong gravity plays a role. Her team also studies the interplay between distant growing galaxies and their supermassive black holes, this coevolution problem that we are very much interested in. So Daryl, thank you so much for agreeing to be our first speaker in this series. I will give the floor to you for 45 minutes. Please post your questions into the chat or into the Q&A, and I will moderate them, mostly at the end, unless there is a clarifying question that is burning to be answered, in which case I might pass that on to you. So with that, I will turn it over. Thank you, Daryl.
Thank you very much for that lovely introduction. And it's a real pleasure to be here and to be the sort of kickoff speaker for this fantastic seminar series. Let me share my slides. So I'm going to be talking today, as Variel mentioned, about Sagittarius A star in all of its multi-wavelength glory. If I have time, I'll come at the very end to having just a quick mention of M87, the first black hole that we were able to create this incredible Event Horizon Telescope image of. And then, as Variel also foreshadowed, I'm a great X-ray data lover. And so what you're seeing here, in addition to this beautiful EHT image, are some of the really spectacular X-ray observations of this galaxy, this supermassive black hole M87 at X-ray wavelengths at larger scales. So that probably I won't have time for because I get too excited about other things, but it's hiding at the end if we end up getting there. So let me start off just by acknowledging the incredible privilege and pleasure I have working with this incredible group of people. This is my research group at McGill University. Today, so these are a variety of graduate students and postdocs, and also some really just amazing undergraduates who work on my team. I will just point out that today I'm going to be highlighting a lot of work from a PhD graduate student in my research group, Hope Boyce. So you'll see lots of Boyce et al. And shout outs to Hope as I work through this talk. She also, along my side, works very closely on the multi-wavelength studies I'll be talking about today. And of course, none of this would be possible without the Event Horizon collaborations, incredible support, incredible scientists, really just a pleasure to work in that community. I'm also a co-chair of the Multi-Wavelength Science Working Group, which is really working very hard to bring in beautiful synthesized data about not only Sagittarius A star and M87, but a suite of other black holes that we target with the Event Horizon Telescope. So many people contributing to what you're going to see today. So I'm here telling you about it with all of my sort of joy and enthusiasm, but it is backed up by really hundreds of scientists working on these efforts. And since I titled my talk, Entering an Era of Black Hole Discovery, let me just begin by saying that this is truly just an incredible time to be studying black holes. My team works on the little ones, so the small black holes that we've seen through via their mergers that emit gravitational waves, and sometimes neutron stars or neutron stars and neutron stars or neutron stars and black holes that also emit electromagnetic radiation. So this incredible first gravitational wave discovery of two merging low mass black holes was awarded the Nobel Prize in Physics, these wonderful scientists. I love this quote by Ray Weiss: "Every day is an interesting day." I think when you're a black hole scientist, it's hard not to feel that just excitement about this science we do all the time. And then, of course, this amazing electromagnetic counterpart to a gravitational wave source that I was very privileged to be a part of the Xray discovery team for. And then, really more pertinent to today's talk, this incredible Event Horizon Telescope image of M87, which won the 2019 Breakthrough of the Year. And really then most recently, the Nobel Prize to these three wonderful scientists, Roger Penrose, Reinhard Genzel, and Andrea Getz, the last two of which have spent their careers studying Sagittarius A star. Another inspiring quote from Andrea Getz, who will be one of your speakers in this series: I hope I can inspire other young women into the field. It's a field that has so many pleasures. And if you are passionate about the science, there's so much that can be done. And this is one of the UCLA Galactic Center group's really amazing videos of 20 years of data tracing stellar orbits around Sagittarius A star, which is the supermassive black hole of interest, not only today, but for your whole seminar series this term. So with that preamble, let me tell you what I'm going to talk about today. I really will focus on Sagittarius A star, and I'm going to in particular talk about variability, so changes we see in the electromagnetic radiation from this black hole, from the accretion flow around it. And I'm going to take kind of a deep dive into understanding spectral energy distributions. So those are the two things I'm going to talk about with you all today. And hopefully that will be fun for everyone to really see some of the nitty-gritty physics that we try to parse out when we look at these observational data. I don't know whether or not you all have access to the Zoom chat. If you do and you feel like just waking your mind up, particularly if it's in the morning and you're just finishing your first cup of coffee, feel free to just toss your response to this little quick multiple choice question into the Zoom chat. Which of the following do you consider definitive evidence for black holes? Radio detections of quasars and AGN. This science really started in the 70s when people started to use radio telescopes to look at supermassive black holes at the hearts of galaxies. X-ray detections of black hole accretion flows. The S-star orbits, those star orbits I just showed you from that wonderful UCLA Galactic Center long-term monitoring campaign around Sag A star, the LIGO Virgo detection of gravitational waves from black hole mergers, the Event Horizon Telescope's beautiful image of M87's black hole shadow, all of the above, none of the above. So if you're feeling chatty and you want to just toss your thoughts into the chat, please do that. It's fun to just have a little bit of interaction with each other and with me, maybe if I get a chance to come back to that toward the end. And I have a second little chat blast later. So toss your thoughts in the chat and share your ideas with each other. So let me start off really here by talking about variability in the context of these two black holes that are really the main targets for the Event Horizon Telescope. So one of those, of course, is Sagittarius A star, which we'll really dwell on today. And the other is M87 that you've already seen this amazing image from. And I show you this plot, which is showing you time. So this is the time scale for variability versus black hole mass along the bottom axis. You'll note that Sagittarius A star is much lower mass, 10 to the 7 times the mass of our sun, than M87, which is closer, up here, close to 10 to the 10 solar masses. And you'll notice that that black hole mass correlates very strongly with the timescales of variability. So Sag A star varies on timescales less than 1 day, while M87 varies on timescales closer to sort of months, sometimes weeks or months types of timescales. That means that when we take images of Sagittarius A star, this source, the accretion flow around the supermassive black hole, is likely to vary over the course of our observations, over the course of a few hours or 6 or 7 hours worth of observations, while M87 is likely to change between 1 day's observations and maybe the observations you take a month later or several weeks later. And these different variability characteristics actually provide very different challenges for understanding what's happening with these black holes. There are lots of other interesting differences between these two, but let me just point those differences out to start off our thinking off today about these two sources. So now thinking about this other physical constraint that we can place on black holes like these, we can look at their radiation at a variety of different wavelengths. So Fariel in the intro said that I do a lot of multi-wavelength astrophysics, which is indeed true. So this is what is called the spectral energy distribution for Sagittarius A star. This is its flux at a variety of different wavelengths. You can see radio millimeter, it really peaks here in the millimeter. This is why the Event Horizon Telescope observes this source at millimeter wavelengths, infrared and X-ray. And you can see here that there's quite a lot of data through the radio and millimeter, and then we sort of run out a little in a few of these places. In particular, you'll notice I don't even have a label for optical. The reason we don't really see anything, we have no data points in here. You can still see these models threading through, trying to understand the physics of the accretion flow, but there's no data in here. And the reason for that is that Sagittarius A star is buried in our Milky Way galaxy, as is our sun, as is our solar system. And so when we try to see Sagittarius A star, we're looking through all the gunk of the Milky Way, and that really effectively blocks out these ultraviolet and optical wavelengths. So we instead leverage X-rays and then infrared through radio wavelengths to try to understand what's happening with this source. And of course, variability and the spectrum of the source might be connected to one another. And here I'm pointing out in particular that in infrared and X-ray wavelengths, these are both shorter wavelengths compared to the ones that the Event Horizon Telescope observes at, we actually see considerable variability. Here in the X-ray, you can see there are several orders of magnitude of variability in the SED. And so we have to understand when we want to try to fit models like the ones you're seeing here, how we can also incorporate variability into our understanding of the radiation physics and the accretion flow around the black hole. So the other thing that multiple wavelengths and different types of sort of physical measures can give us is an opportunity to start out at large distances away from the black hole and sort of march in closer and closer to the event horizon and try to understand what all those different physical scales look like and how they interact with one another. Remember, supermassive black holes, though they sound spectacular and huge, are actually physically very small. Probably many of you have seen that beautiful XKCD comic where they took the image of M87 from the Event Horizon Telescope and put a little model of the solar system. And I hope your mind was blown that here's this incredibly massive black hole, and it's not even that much bigger than our solar system. So Sagittarius A star, I've forgotten my good little metrics, but Sagittarius A star is less massive and less large in many ways than M87. And I think its orbit, goes out, or sorry, its last sort of photon orbit is also sort of roughly the scale of the solar system. I can't remember exactly how it is, but big it is, but it's smaller than M87 and something like solar system size. And the reason I bring that up is that when you're trying to look at these different size scales, you really have to be able to look from something that is, galactic, almost galactic in scale, to something that is very, very tiny solar system in scale. So this is not quite that spread. We're looking at a plot here of the Schwarzschild radius, which is sort of the rough metric of the size of the black hole. So this is the distance away from the black hole in units of Schwarzschild radius. And then along this axis, the one that's on the right-hand side, you're looking at the mass accretion rate, how many masses worth of material fall into the supermassive black hole per year. And here you're looking at how dense that material is, sort of a rough metric of what the density of electrons in particular in the vicinity of the black hole looks like. And you can see as you move in toward the center of the accretion flow, you see larger and larger densities. And we can use a variety of different metrics starting from the outside. We can see stellar winds. So those stars that I showed you, that beautiful video orbiting around Sag A star, those stars have very strong winds and they're contributing mass into the environment, and that mass then can fall onto the supermassive black hole. Then we have X-ray metrics. Really looking, I'll talk a little bit more about this, but we see hot X-ray gas. It's that stellar winds are heated by feedback from the stars and from the black hole and other phenomena, and that becomes very, very hot, that gas, and so we can trace it out in X-rays. Then we can move in. This plot is taken from some nice work done by our colleagues working at infrared wavelengths, and they were really emphasizing this sort of midpoint here, where they were looking at objects orbiting Sag A star and how those objects experience drag forces and how that changes their orbits and can give us a sense of what the electron densities, what the mass densities are near the black hole. Then as you get even closer, you can start to look at the rotation measure. How is the material near the black hole impacted by scattering and by magnetic fields? Polarization. Hopefully some of you also saw the beautiful polarization results about M87 that came out just earlier. I guess it's now last year in 2021. So polarization can also help us trace magnetic fields. And then we get down to the horizon scales and we start to really be able to look at what's happening, what is the geometric size of the black hole, and what could that tell us about the accretion flow really, really close to the event horizon. So we try to use all these different wavelengths, all these different techniques to understand what the conditions are, what the physical conditions are near the black hole. And I'm really going to spend the bulk of my time today talking to you all about a beautiful multi-wavelength campaign. As I mentioned, this data was analyzed by my graduate student, Hope Boyce, but we've got amazing X-ray data from the Chandra Xray Observatory, also NuSTAR, and sometimes SWIFT join in this campaign. The Spitzer Space Telescope has done some really beautiful coordinated observations with Chandra at infrared wavelengths, and then connecting it up to these amazing observations that are done by the Event Horizon Telescope at submillimeter wavelengths. This is a little image of the ALMA array in Chile. So starting out with the X-ray observations, just to help you understand some of the phenomenology I'll be talking about here. This is a little montage of images from the Chandra X-ray Observatory. What you're seeing here is an X-ray image of the Galactic Center. Sagittarius A star is helpfully marked out. You can see here that there's some extra, the dark colors here are showing you excess emission. And this is what we call the Bondi radius. This is roughly the sort of gravitational capture radius for the supermassive black hole. And you can see within this capture radius, there's quite a bit of hot gas. If we zoom in over here on this panel to the right on the top, you can see here again, dark means there's excess emission. And you can see here that this excess emission actually has a slightly elongated structure. We think this is an interesting interaction between the gas and those stars that are orbiting around the supermassive black hole. And the green contours are showing you what this emission, how it looks just specifically when the black hole is flaring. And you'll notice that those green contours are much more circular. They're not elongated in the same way that the distribution of colors in the background are. And so we think there's something qualitatively different going on when you just are seeing a passive quiescent state for the black hole and some bright flares. Then down along the bottom here, this is just a nice, pretty artistic sort of rendering of what's kind of how these different size scales fit together in the Galactic Center. This is a beautiful multi-wavelength image from, I think it's from Spitzer, Chandra, and Hubble of the Galactic Center. And you're seeing sort of all of these different wavelengths combined together. 20 parsecs is the size scale here. When we zoom in a little bit closer, now we're on a half parsec scale. Just as a rule of thumb, a parsec is roughly the distance between our sun and the next nearest star, very hand waving. But here you can now start to see those sources that I showed in the pretty picture from the UCLA team. These are these stars that are in orbit that the Gensel group and the Getz group have been tracing out, as I said, for more than 20 years now. And you can see there's a broad stellar disk. You can see this sort of oblong shape is mirroring this oblong shape of the X-ray gas. And we think those two are related to one another. And in the middle, the distribution of stars and the distribution of gas is a little bit more spherical. Zooming in here again, you can really see that they're co-located. This hot X-ray gas and these S stars that are orbiting are occupying the same physical space. And this is one of the reasons we actually think it is the winds from these stars as they get pushed off the stars themselves that are actually creating this hot X-ray gas that then subsequently accretes onto the supermassive black hole. Now looking here, an astronomical unit is the average distance between the sun and the earth. So you're here now looking on much, much smaller scales at what we think might be happening based on a Sgr MHD model of the accretion flow and maybe a jet down near the supermassive black hole. So this is just to try to put all the pieces together. We're really now going to delve in and talk a bit about these X-ray flares, and then I'll come back and talk about the broadband spectral energy distribution as well. So this is that beautiful multi-wavelength image of the Galactic Center. You can see here the supermassive black hole is buried down in here, and it's very difficult to see it directly because of all this other gunk in the way, as I've already mentioned. But we are lucky with X-rays because they actually can show us, just to let this video run one more time, they can actually show us this black hole without so much obscuration. X-rays are very, very short wavelength. They don't interact as much with dust and other things in the galactic plane. And so they managed to get through all of that stuff and come to us and show us a little bit about what's happening at the site of the black hole. I will make one just very quick clarifying thing here. You'll notice that there are two things happening in this X-ray video. One is a persistent X-ray source, which you can see here, and then there's that bright flash. So that persistent source is actually not the supermassive black hole. It's a neutron star, very close to the supermassive black hole that was discovered in 2013. And around that same time, while that neutron star is there looking bright and impressive, Sgr A had that very bright flare. So this is now a static image from this same little movie. You can see here, this is that magnetic neutron star circled in yellow in all of these panels. You'll notice it had a bright outburst and then faded, and it still continues to fade and is almost beyond detection now in the X-ray. And this is that very, very bright flare from Sagittarius A star. So when we have this static image, we can see these are two individual point sources. They are two separate sources. This is the supermassive black hole, and this is a neutron star that's actually at pretty large distances away from it, despite the fact that they look so close in the image. And I can also show you what this, if we just subtract that flare emission off, I can show you what the supermassive black hole looks like in so-called quiescence. So this is when it's not actively flaring. And then this is a second bright flare at the bottom. This one was in 2013 and this one was in 2014. So we can use these very bright flares. This is a light curve now. So this is the brightness of the flare as a function of time. And you can see here, this is the magnetar is in orange once again, just kind of bubbling along in both of these images. This is the September 2013 and the October 2014 flares. And this is that very, very bright flare. Don't worry too much about the colors right now. Just focus on this black line. This is showing you that flare, which is, many factors, very, very, very bright compared to the quiescent emission, which is bubbling around long down here at the bottom. The two colored subflares are when we just take that flare and we bin it up into two different energy bins to give us a sense of kind of roughly whether the higher energies or the lower energies are dominant during the flare. The blue is the slightly higher energy emission. And so you can see indeed that this flare has slightly more high energy emission than lower energy emission. And this is that second flare that happened in 2014. And it might look a little bit piddly here on my slides, but I should say that this is, if it weren't for this flare, this would be the brightest flare we'd ever seen from Sgr A. But it turns out that this one was just so bright. It was 400 plus times the quiescent emission from the supermassive black hole. And so a really, really, really just whoppingly bright flare. And we wanted to plot them on the same scale so you could actually compare them 1 to 1, which is why this one looks a little bit less impressive. For scale, this is about 2 hours in the time axis here. So this bright flare lasts for several hours. And you can see has very interesting substructure that could either be due to radiation physics or gravitational lensing. There's a lot of possibilities for what might be making that interesting morphology in the flare. We can take these flares. So it turns out Sgr A has an X-ray flare roughly once per day. That's a statistical average. It can go many days with no flares. And then sometimes it'll just go pop, 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 pop all at once. But on average, it has an X-ray flare roughly once a day. They're usually much fainter than these two I'm showing you here. But there was a wonderful campaign in 2011 from the Chandra Xray Observatory that tried to observe Sagittarius A star for a lot of time over the course of one observing season and really collect a statistical sample of flares. And so that's what you're seeing here. This is beautiful work done by Joey Nielsen that helped pull together this population of flares. And you can see there's a trend line here, kind of just trying to look at how the total amount of flux under the flare correlates with the duration of the flare, how long the flare itself lasts. And so we took this statistical sample and compared these two very bright flares. This was the point I was making before about how these two flares are really bright. I guess there's maybe a third one here that's as bright. This is probably the one that Mike Novak wrote some really nice papers on early on in the campaign too. So these three flares make up the brightest ones we've ever seen. And despite the fact that they look a little bit off this trend line here, we've looked at these flares in a lot of detail. In particular, we've looked at their X-ray spectra. So this is the spectrum where instead of taking the flux and spreading it out versus time, we're now taking the flux and spreading it out in bins of energy. And we want to see, like, is there anything interesting at the high energies versus at the lower energies? What is the shape of that spectrum, et cetera? And you can see this is Sagittarius A star, this is the magnetar, and this is that quiescent emission. And so from the physical parameters, we can try to understand what we call the power law fit to this flare. And we can compare that to the magnetar and try to convince ourselves that we can analyze this flux without contamination from the magnetar. And when we do this spectral analysis of these two bright flares, we've nicknamed 1 and 2. This is that third very bright flare in the analysis from Mike Novak, and a series of other really nice works from Gabriele Ponti and Delphine Parquet, and again, Mike Novak, who have looked at these different flares. Just to focus you on a couple of these parameters so this table doesn't bend your brain. One of the things that we like to think about in a spectrum is what the power law slope of that spectrum looks like. And so we characterize that in X-ray terms in terms of this so-called photon index, which we indicate with a capital gamma, gamma. And so you can see here that though those two looked a little bit off that trend line, spectrally, they're very, very similar. And we've seen this again and again when we look at flares, that they just really look very similar from one to the next. And when we look at flickering and flares at infrared wavelengths, they also have a very similar spectral index. If you convert from one of these to the other, these are actually quite consistent with one another. So what can we learn about this? We can look at the total energy contained if we make some just very simplifying assumptions. I won't walk you through this equation right now, but if you make just some very, 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 very simple sort of physical arguments about the volume that you could use to contain this amount of magnetic energy, if you say the magnetic energy is roughly equal to the X-rays, you find that the size scale for that volume is something like 6 to 10 gravitational radii. So that does not necessarily mean that the X-ray flares are coming from 6 to 10 gravitational radii. You know, maybe you've got some little eddy in the accretion flow far away from the supermassive black hole. We can't distinguish those things with the X-ray data alone, but this is very interesting. So we see these flares very often. It looks like if they are coincident with the supermassive black hole, they're coming from radii that are very, very close to that black hole, something really close in toward the event horizon. And I'll come back to this later, but there's an infrared interferometer that's been doing observations looking at polarization periods and other things, and they find variability near the supermassive black hole at a very similar size scale, something like 6 to 10 gravitational radii again. So this is starting to get really interesting and starting to point to this flaring phenomena being really kind of a horizon scale or potentially horizon scale output from the supermassive black hole. All right, so that's X-ray. I'll come back to infrared just a little bit. I want to say I had a wonderful postdoc work with me on doing analysis of this very bright flare at radio wavelengths. So this, you'll recognize the funny shape of this bright X-ray flare in green here. We also had some beautiful data from the Very Large Array at the same time. Dan Capilupo was a postdoc in my group at the time working on the light curves at radio wavelengths. You'll see here that when we observed this at radio wavelengths, we wanted to know, is there any kind of leading or lagging? Like, do we see the X-rays first and then the submillimeter or the radio emission second? You know, what can we say about how these things are correlated with one another, if they are correlated at all? The gray bands on the two sides, once again, this is a light curve, we call it. It's time versus total flux. The gray bands on the two sides are when the observations are less reliable because you're very near the horizon. You have a little bit less visibility at those times. And so you can see we trust these data out in the gray positions a little bit less. So excited when we looked at these data. We wanted to say bright X-ray flare, you know, we can measure the time delay to the radio emission, but we have this unfortunate thing that the peak in the radio emission comes during these times when we trust our data less. And also this last data point is just, you know, the last bin is often a little bit unreliable. So we're not completely confident we caught the peak of this radio outburst. And so we can still try to sort of say, okay, so if we assume this is the peak of the radio outburst, what is the time delay between these two phenomena? These two peaks in the X-ray and then in the radio. And it looks like the cross-correlation peak. This is a cross-correlation analysis you can see here. If you look at the comparison of these two, you can try to measure what we call a time lag, and that appears to be at about 125 minutes. So this is interesting, but I don't want to get you too excited about it because we ended up finding that if we took this very bright flare, okay, so we had not only this one day of radio data, we had lots of days of radio data, and we had this bright X-ray flare. So here's this bright X-ray flare. We wanted to convince ourselves that this was meaningful. And we said, well, what's the sort of simplest thing you could do to try to convince yourself that this was meaningful? So you can take this X-ray data and correlate it against radio data that's from different days, days where there should be no correlation. And if you don't see a correlation, then you start to think, wow, this is really compelling and neat. If you do see a correlation, then you start to worry a little bit, because it turns out Sgr A at radio wavelengths is almost continuously varying. So if your radio source is continually varying, and then you compare that to some X-ray flare, maybe you'd kind of always see a correlation. And indeed, that's sort of what we found. This is a plot of those correlation analyses. And what you'd like to see, the colored boxes along the diagonal are showing you dates that are actually simultaneous. So this is when the radio data and the X-ray data are actually taken at the same time. And then these are different eras of X-ray data just correlated against absolutely all of the dates. And what you'd like to see, this is that bright flare, what you'd like to see is no trend in these plots on the September 13th data row. Only a trend in the colored box and no trends in the off diagonal boxes, but instead we see strong trends in all those boxes, indicating, of course, that the constant variability of the radio source makes it really hard to definitively connect that radio outburst to the X-ray outburst. So still compelling and interesting, but not quite as definitive as we'd like. Still trying to draw a few, at least sort of instructive things from this data. It does appear that the short wavelengths come a little bit before the longer wavelengths, which would be consistent with some of our simpler models about an expanding blob or a jet potentially from the supermassive black hole. And just to emphasize here that we don't have the highest quality data, and in order to improve that, what we'd like are very, very long light curves where the two data sets are fully simultaneous over long periods of time, where you see the rise of the flare, the decline of the flare, and then quiescence again. And if you see that at two different wavelengths, you become more convinced that one and another are actually connected to each other. So we're still working on this. This is very interesting, and you'll see some great results, I think, out of some multi-wavelength studies coming up in the next sort of 4 to 6 months, trying to really push on this a little bit more. But this notion of getting long, fully simultaneous light curves is really what drove this beautiful campaign that my grad student Hope Boyce and Gunter Witzel and quite a few other people have been working on. And so we somehow, I don't even know how we did it, but we somehow convinced the Spitzer Space Observatory and the Chandra X-ray Observatory to take their two space telescopes and point them toward the Galactic Center and monitor the Galactic Center for very long periods of time, completely simultaneously. So these light curves are roughly 20 to 24 hours long, which means we had two space observatories staring at Sgr for 24 hours at a time. It turns out that those two observatories, Spitzer is no longer in operation, but at the time could only do this for 2 weeks per year. And so we had beautiful campaigns over the course of several years, really staring at Sgr, trying to understand what's happening with the flaring behavior. NuStar joined in this campaign as well, as did this wonderful ground-based interferometer known as Gravity and the ALMA Observatory. And so ALMA is one of the elements of the Event Horizon Telescope Array. This is not Event Horizon Telescope data, it's data just taken by ALMA alone. But you can see now we've got very high energy X-rays, X-rays from the Chandra X-ray Observatory at a little bit lower energy, infrared light curves, very, very long infrared light curves from space. So this is from the ground, this is from space, and beautiful submillimeter light curves from ALMA on a couple of different dates. And so this is a really beautiful data set that my grad student Hope is just about to publish. And we got lucky, we did pick up one flare. So I'm really going to focus on this. This data was collected in 2019. And you can see here we've got some really interesting data that's spanning quite a few wavelengths, and we can try to take a peek and understand what's happening with the spectral energy distribution during these flares. So this is just a summary of these campaigns. We have 6 observations that are fully simultaneous. These 2 are taken in 2019. And the data sets contain, 155 hours of simultaneous X-ray and IR data. This is just an incredible data set alongside NuStar, Gravity, and ALMA. So these are those cross correlation plots. So these are the light curves just zoomed in on that one flare in 2019. And the fates, of course, are never kind to multi-wavelength campaigns. You can see this is the NuStar data, Chandra, Gravity, ALMA, and Spitzer. And where do we see a gap? Right in the middle of the ALMA data. So we'd love to be able to see what's happening in the submillimeter here. But this is a gap, probably just the evening came, or another observation was taken. And so we did not actually capture the full duration of this flare with the ALMA data. But again, we can kind of say, okay, well, maybe if we're seeing part of the peak, or if we extrapolate and try to figure out what the shape of this flare might have looked like, we can still use this in our analysis. We take the Spitzer data as our sort of basis for comparison because those light curves are very, very nice and very long and very even. And we correlate each one of these wavelengths, New Star against Spitzer, Chandra against Spitzer, Gravity against Spitzer, ALMA against Spitzer. And you can see here that the red line is showing you no lag, no lead or lag between wavelengths with 1 sigma error bars here. So not surprisingly, the two X-ray data points are sort of similar. You can see that the IR and the X-ray also seem to be very close to simultaneous. And you can see here that this sub-millimeter data point from ALMA, if we make a few simplifying assumptions about what happens in the data gap, that again, the long wavelength seems to be kind of lagging behind the shorter wavelengths. And so this is a plot summarizing these data and trying to just make this point. This is New Star versus New Star and Chandra. These are again, each compared to Spitzer. And you can see these three look fairly simultaneous. And then we have this potential lag between the ALMA data and the shorter wavelength data. Here again, we're putting upper limits here only because we don't have complete coverage throughout that region. So I'm going to dive in just a little bit more and talk about these data and how we can use them to try to understand what's happening with the timing and with the spectral energy distribution of the supermassive black hole. So the timing has to do with these sort of flares and the leads and the lags and when the radiation, when the energy is injected and how that energy evolves over time. And the near IR spectral index is one way of trying to understand what's happening with the spectral fitting. Okay, so I'm going to dive in here. This is the main like radiation physicsy part of the talk. So here we go. Bear with me. These are some amazing slides that my grad student Hope Boyce has put together to try to help us visualize how we use multi-wavelength data and multi-epoch multi-wavelength data to understand what's happening with the radiation in the galactic center. Okay, so this is what a spectral energy distribution of Sag A star might look like. You're looking at intensity versus wavelength, basically. We take these data points and we fit them with model spectra. So these are model quiescent spectra, no flares happening. And I'm just going to walk through and explain these different components to you so that you have some sense of the physics that drives this spectral energy distribution. So these are the things I'm going to draw on. Synchrotron radiation. This is electrons spiraling along magnetic field lines. As they are accelerated in those orbits, they emit radiation, which we call synchrotron radiation. You can also have Compton and inverse Compton, but let's just talk about inverse Compton here. You have a population of energetic electrons. A photon comes in and interacts with these electrons, picks up a little of their energy, and gets moved to a shorter wavelength, higher energy photon. Compton would be the opposite, where you have photons hitting electrons and heating up the electrons, moving them to higher velocities. And then Bremstrom radiation, which is also known as braking radiation. You have a proton, some heavy object, an electron interacts with it, a free electron interacts with it, and it's accelerated once again, and that emits some radiation. So we're going to work with these radiation mechanisms and try to think about this observed spectral energy distribution for Sagittarius A star. So here's our black hole. Here's Sag A star smiling out at all of you. In the accretion flow around Sag A star, we have some very hot electrons. So we see some synchrotron emission from thermal electrons zooming around. There are magnetic fields threading this accretion flow, and that's what leads to this sort of synchrotron type radiation. And we can plot here on our SED what that synchrotron spectrum might look like. So here's a picture of just the solid red line is what we think synchrotron spectral energy distributions will look like for just a heated plasma in the presence of magnetic fields. Okay, that's good. So now we also think that there are some scattered photons running around, and those scattered photons that interact with this energetic electron distribution can get inverse Compton scattered. So this is where the photons pick up a little energy from the electron distribution, and that gives you the second bump here that's plotted out here as a dashed line. Okay, so in the quiescent spectral energy distribution of Sag A star, you know you probably have these two components. They fit the data really nicely. Synchrotron just from thermal electrons in the presence of the magnetic fields of the supermassive black hole. And here you have some inverse Compton scattering up to higher energy. So this is giving you centimeter, so radio, submillimeter flux, and then those get bumped up to shorter wavelengths, near infrared and X-ray. So higher energies, shorter wavelengths. All right, so now let's imagine we have some kind of a flare, some sort of energy injection, some acceleration event. These are what the flares I've been talking about. And that does a couple things. It can compress, if that's a kind of a compact event, it can compress the electron population and also heat it. And so you have some acceleration event, it impacts your electron population. And now you see a second synchrotron contribution from a non-thermal population of electrons. We think these flares, those slopes, those photon indices I showed you are indicative of non-thermal processes. And so now we have a little extra synchrotron emission coming from this non-thermal process. And we plotted that as a yellow line here. So we've got these three components combined together during flaring events, and we can start to kind of see, okay, what does quiescence look like and how does it differ from what we see in the spectrum when we have a flare or another energetic kind of injection. Taking 1 minute and just zooming way out to those larger scales I was talking about before, out near that Bondi capture radius, this is now very far away from the black hole. All that other stuff I was talking about is very small in here. Out at larger radii, you just have this sort of pool of hot gas from those stellar winds or from other phenomena. And that has a thermal Bremstrom spectrum where you have, protons and electrons. They're still in a hot plasma. This is often X-ray emitting. So they're dissociated from one another and just interacting out in this very, very hot plasma, and that gives you this thermal Bremstrom component, which is typically out at the highest energies at X-ray wavelengths detected by Chandra and NuSTAR. So now this is the spectrum I showed you on that first slide, where the black line is showing you the combination, the addition of these components. This was that synchrotron, this is that inverse Compton component, this is that non-thermal synchrotron component, and this is the thermal Bremstrom component. So these are all interesting things that we have, or models that we think we can use to understand what's happening with the SED. So now we have this, we want to understand these flares a little bit better. So as I mentioned, a flare might give you this sudden strong acceleration, and that can give you this extra synchrotron component. And so those are just to remind you what we're talking about. What does that do to the SED? So that takes the standard quiescent SED, gives you a second component here, and that pushes, in particular, some of these points near the infrared. Remember, I said the infrared spectral index can help us understand what's happening during flaring events. So if we just have synchrotron emission, maybe we take the synchrotron component we had, we add another component, or we push the whole synchrotron component up toward shorter wavelengths, higher energies, and we slightly shift our spectrum. So instead of having this infrared slope being falling, we see the infrared slope is rising. So this is one signature we could look for. Maybe after this event, you also see some interesting synchrotron self-Compton photons. So here you have photons coming from this accelerated electron population. Those photons interact with other electrons just at slightly larger radii and cause them to be excited, cause them to be accelerated. And then those emit higher energy photons as well. These are known as synchrotron self-Compton or SSC photons. And so you may have an extra component from this synchrotron self-Compton phenomenon. So now we see, okay, this is interesting. If I add in a synchrotron self-Compton component, I've shifted the SED at infrared wavelengths again, and now my near IR slope is back to being a falling slope instead of a rising slope. So now I have some kind of a lever arm to understand whether or not I do or do not see this synchrotron self-Compton component during flaring events. And of course, then the electron density, since all of these are interactions between photons and electrons, the electron density matters. If I toggle the electron density up and down, I can also start to shift how much of a contribution I get from each of these different components and start to understand how that's going to affect for perhaps this same near infrared slope metric. And so you can see now this becomes very challenging for data to be able to constrain all these different parts of the model simultaneously. And so what we try to do then is to, and then let me just add one more complication. So not only do we have these different components in a static system, of course, the whole source evolves. So imagine you've got the supermassive black hole, a flare goes off, that flare injects a bunch of energy into the accretion flow, and that accretion flow then cools off again. So there's evolution in the spectral energy distribution, which is why you need both the timing and you need the spectral information together in order to understand the different physics that are the different radiation physics and other accretion flow physics that are happening near the black hole. So for example, we had this electron population, we had a flare, we compressed some of those electrons, we created a non-thermal distribution for a little while. So we have both a non-thermal component, but also the compression happening. And then maybe an adiabatic expansion happens over longer times. And so we might be able to include that evolution as a part of our modeling effort. Okay, so what does that evolution look like? You may start off with this synchrotron, then you compress and add a non-thermal component. You get this yellow curve here during that epoch, and then the whole thing expands and cools back, but maybe it's at a slightly higher luminosity or temperature than where you first started before the flare. So this kind of evolution of the SED is another thing we can look for when we have these very nice long light curves. And you can also see they have different multi-wavelength properties, with the compressed spectrum looking a little bit higher energy than the uncompressed or adiabatically expanded spectrum. Okay, so these are these beautiful multi-wavelength data we've gotten. How can they help us constrain models? So this is the kind of effort, again, just in this pictorial representation that I've been offering you. If I imagine right at the peak of the X-ray flare here, which is marked off as a 1, maybe I have this extra, the synchrotron self-Compton component, this non-thermal component, because that acceleration event has just happened. And so maybe I model my SED as looking like this. And then I want to understand, okay, so I have the spectrum, I have an idea of what it might look like. What does it look like later? Can I also model this peak that we think we might be seeing in the ALMA data and the sub-millimeter data that is at some time that seems to occur at some time slightly later? And so maybe that's what this is, that distribution we had before in gray, and maybe it adiabatically expands and evolves in time to give us this SED slightly later. And if we can connect these together and convince ourselves that they are a good model of the light curves that we observe, now we might just be able to start to argue that if we can take an event horizon telescope image, we can see this flare at horizon scales, and we can trace it out and connect it to these multi-wavelength data that we're collecting, where we cannot pin down the actual radius of that radiation as well as the Event Horizon Telescope can. We start to be able to argue that these flares that we've been observing for years at many wavelengths are truly horizon scale phenomena. So this is the promise, this is the hope of doing all of this multi-wavelength legwork and then trying to link it together to the incredible capabilities of something like an Event Horizon Telescope. Okay, so we don't only do science in pictures, though it is very fun. So this is actual plots from the work that my grad student Hope is working on. These are a few of these different models that I've walked you through, and then a look at how they might evolve in time. I'm not going to go through this in gory detail, but to suffice it to say, you can see on this plot here that we can actually do a pretty nice job of modeling some of the actual data points we have from those beautiful multi-wavelength campaigns, and start to really try to understand which models these data prefer. In this case, our best fitting model is one where the sub-millimeter flux comes from optically thick synchrotron emission, and the near infrared and X-ray come from synchrotron self-Compton emission. And then we can evolve that just through the simplistic notion of adiabatic expansion and see what it looks like later in time. So the orange is the SED that we would expect to see right at the peak of the infrared and X-ray flares. That was my little number 1 from before. And the purple SED is the one that you might expect to see sometime later near the peak of if we've caught the peak of the ALMA emission at sub-millimeter wavelengths. And that occurs about 35 minutes later. So this is very, very interesting. It is sort of early days in being able to do this beautiful SED fitting. There are folks working at the Max Planck Institute very hard on these spectral energy distribution models, and those of us really trying to throw data at the problem. So again, I'm going to skip over this just for lack of time, but these are some of the same conclusions that I just walked you through on those plots, and you can see them in my slides later if you are curious and interested. I will say that this question about electron density, which I'm starting to kind of hit down here at the bottom, and the optical thickness of the accretion flow, is very tricky to parcel out and figure out exactly what's going on. And so as a good bona fide observer, I will just leave with the conclusion that you always make in data papers like this, which is we just really desperately need more data. And so we're continuing to try to really push hard on these multi-wavelength campaigns. And as I emphasized in that first slide, for Sagittarius A star, since the time scales of these changes are over the course of several hours, it means that the data cannot be one observation taken today and another observation taken next week. They have to come together. They must be fully simultaneous. And this includes our coordination with the Event Horizon Telescope. Otherwise, we lose all of this richness that I've been trying to show you and help you see how much radiation physics there is to try to disentangle in the accretion flow around Sag A star. So for Sag A star in particular, these simultaneous multi-wavelength campaigns are absolutely crucial. All right, I will just now, oh, this is the second chat blast. I just want to talk very briefly about horizon scales and then I'll pipe down. But let me just say here, oh, so this is your second chat blast for people who have started to space out because that was too much radiation physics for you. This question is, what do you think is a really great test, a legitimate test of general relativity? The precession of Mercury's orbit around the sun, gravitational lensing, S-star orbits around Sag A star, in particular their precession, LIGO Virgo detections of gravitational waves from black hole mergers, the EHT image of M87's black hole shadow, all of the above or none of the above. So for those of you who are in a voting mood or a chatty mood, please throw your thoughts about that into the chat. Okay, and let me just say, I've already tried to make this case to you a little bit, but these two instruments, the Event Horizon Telescope and the VLTI gravity instrument down in Chile are really, this is near infrared interferometer. This is a sub-millimeter worldwide global interferometer. And these sorts of efforts are really pushing down so we can start to try to understand the accretion physics down at the smallest scales. The gravity group has seen some basically wobble in their image, which they've attributed to a hot spot orbiting around Sagittarius A star. We've tried very hard again to coordinate some of these multi-wavelength campaigns against both EHT and gravity observations. And so really stay tuned. This is extremely cool and exciting and rich. You saw that gravity light curve that Hope has been analyzing, and we hope to have more of that rich data and observations to come. And I will say that Sag A star is a beautiful source to study with these really phenomenal instruments. M87 is no slouch either. M87 drives this really amazing, huge jet, which I won't have time to talk about today, but really offers just gorgeous images. And this is a plot that shows you a little bit of the overlap we have between these really spectacular campaigns and the Event Horizon Telescope campaign, specifically on Sag A star in 2017. So this is really exciting. You can see here, this flare actually turned out to be not true. So cross that one off psychologically, mentally. But we do have an X-ray flare that is very close to the EHT observations. And hopefully you'll all hear more about that coming up soon. I'll just leave it off with this summary here, just saying that I think these flares, I think these simultaneous multi-wavelength campaigns are absolutely key, not just to pinning down individual wavelengths, sort of phenomenology and properties, but really linking them all together in this really important framework so we can understand the physics of the accretion around the supermassive black hole. And I think this variability is going to be just fabulous if we can ever have the universe behave properly and give us beautiful, completely co-eval multi-wavelength flare data. It's a serendipitous capture, and so we really just have to keep trying until we get the data that we hope for. All right, so I am going to wrap it up, I think. I have a few slides on M87. You can't not love M87, but I'm just going to show you that M87 is beautiful. It's beautiful by the, when observed by the Event Horizon Telescope, and it's beautiful when observed by every other observatory you can get your hands on. So I was very excited about this work, really trying to connect horizon scales all the way out to the very, very largest scales. But I will leave that for another talk on another day. And for today, I'm going to skip to my very, very, very last question slide and just tell all of you that it's a pleasure to be here. I absolutely love black holes. I could talk about them all day long. If you love black holes and you have questions from this talk or you want to give us a little bit of feedback about it, please don't be shy. Here's a link that'll also appear in your Zoom chat in just a second here. Everybody that's a part of this effort would love to hear from you. So I'm happy to take some questions now. And if you've got feedback outside of this forum, please share it with us.
Thank you so much, Daryl. That was an excellent talk, excellent overview of the spectra, the variability, flares that we see from Sag A star, and the unique window that multi-wavelength campaigns offer us into the nature of that variability. We got quite a few questions, so I will go in some order and read them out to you. And in the meantime, as Daryl just mentioned, please do provide your feedback. We've been doing several years of these Black Hole PIRE webinars, and your feedback has helped us with the format and topics and making it accessible. So we really do value it. The link is in the chat. We would appreciate it. Just a couple of minutes of your time. So let me go in not the order that the questions came, but some topical grouping. One of the questions from Martin is, should not the flares from Sgr A be always lensed and not just sometimes? I believe you said in your talk, sometimes we see, or we think we see signatures of lensing, or is it a matter of resolution or alignment? So are flares always lensed?
Yeah, I hesitate to give any answer that includes the word always in it, because Lord knows the universe is full of things we don't understand. But is lensing important? I think the answer is absolutely yes. So this is some really nice work that's been done by Jason Dexter and his collaborators, in particular Jimenez Rosales, through the gravity collaboration. So these are looking at some of these infrared phenomena that seem to really be coming, they don't have quite the resolution the Event Horizon Telescope does, but they do have beautiful resolution. And what we can see is that they're I called it wobbling. I'm sure that's not really what they would want me to call it, but you can see this is sort of like the motion of the centroid of the brightest part of the emission. I was probably doing that in the wrong direction, but the going around, and they can actually get that centroiding very, very accurately. And you do need lensing in the models to really understand what's happening. And you can see, as I mentioned, some of this work going on from Jason Dexter and from other people in the gravity collaboration. We haven't reported any kind of, I want to call them that, from the Event Horizon Telescope yet. Please hold on for that. It turns out it's very, very hard to study a source that varies on short timescales. And so everybody's been working really hard on that for the modeling. As I mentioned, the X-ray flare could very well be described by lensing, but that's not a completely unique interpretation. One of the challenges about understanding these flares, at least from the X-ray perspective, is their duration. I told you they last for several hours. Energy injection, heating up a population of electrons with a little burst, say a magnetic reconnection burst, that happens, on very short timescales, and they cool really fast. Like, these flares should last minutes, not hours. And the fact that they last hours means that there has to be some kind of constant energy injection. And we struggle to really make phenomena that are injecting energy over those 2-hour timescales, very long timescales. And because of that, you can also come up with some sort of variable injection mechanism that causes that double peak in the X-ray flare. It doesn't have to be lensing, but if it's a persistent source, then you really might like to evoke lensing to get that interesting double peak structure. So lots of richness. Definitely lensing seems like it's important. Is it unique? Must it always be there? I will not make a firm statement about that.
That's great. If I can add, from the theory point of view, we think lensing is always there, but the proximity of the emitting region to the black hole, of course, determines the degree of lensing. And the fact that we see it in the data, or at least not uniquely, but one interpretation of what we see in the data is lensing, is also great. So
yeah, I just pick that up one more time,
yeah,
and just to give Daryl and her group a shout out. There's some really nice work done by Ball et al., who was a member of your team for a while, who worked on these trying to understand the lensing at trying to generate multi-wavelength light curves from models that did include things like lensing. And so I think this has just been moving very fast paced. There's a lot of really beautiful work being done on the theory side to try to create simulated light curves that we can then also compare with the observations to help to sort of it's a more like kind of pure GR physics generation of light curves to compare to the data, rather than this SED modeling that I spent a lot of time on.
Thank you. I really wasn't fishing for that, but it's just always the the nice synergy between the observational point of view and the theoretical point of view.
No, I didn't mean that you were. I just meant it's really exciting. There's a lot going on there.
Absolutely. So another flaring question. You mentioned that it happens, the flares occur once a day. Is there a reason for it?
Oh, that's a really good question. Yeah, so I think that I don't have a super great answer to that. So let me give you a hand waving answer to that. So one of the models, not a unique model, but one of the models we use to describe flares in the vicinity of Sagittarius stars, this thing called magnetic reconnection. We see it if you've ever seen those beautiful, say, SOHO videos of the sun, right? You see these magnetic loops off the surface of the sun. When the magnetic fields get too close together, they can do this thing called reconnecting, which is, that one of those kind of percussive energy injection mechanisms. So if there were a reason that as you orbit this supermassive black hole, you wind the magnetic fields and you basically build up that magnetic energy, and it can only kind of hold so much before breaking, that could give you a characteristics timescale, maybe. Another possible, just to help parameterize our ignorance about this stuff, another possibility for flares is actually tidal disruption of, kind of kilometer-sized bodies. That's a little bit harder unless you have a sort of pretty uniform population of kilometer-sized bodies that fall into the black hole and get shredded apart with some regularity. But I also want to just emphasize the statement I made when I was talking about the regularity of these flares, that though statistically we see them on average once per day, we have epochs where, days go by in our observations where no flares happen at all. There's nothing going on. And then other days where we have bang, flare, bang, flare, bang, flare. So they are not a consistent once per day kind of phenomena. It's just on average, as we observe, we see them kind of popping up roughly that frequently.
Thank you. So switching to some spectrum-related questions, there is one that asks, what are the energy bins used to split up the high and low components? Is it the distinction between hard and soft X-ray bands or something dependent on Chandra's energy bands?
Yeah, no, that's a great question. So the ones I was showing are just hard and soft, and we have a sort of, different people define this differently depending on the kind of study that they're doing. For Sagittarius A star, in part, so I lied to you all a little bit, I'll just confess it now. X-rays are obscured from the Galactic Center, and the lower energy the X-rays, the more that obscuration it impacts our observations. So Chandra is sensitive as an observatory from 0.5 to 10 keV, roughly. It's lost some of its sensitivity instrumental reasons over the years, but it still can observe over that whole range. When we show you images of Sagittarius star and X-ray data and flares and things, we're cutting off everything from 0.5 to 2 keV because it's just too absorbed. Those lower energy photons are being impacted by all the dust and gas and nonsense between us and the Galactic Center. So Galactic Center observations are almost always preferentially showing you the higher energy band from Chandra, so sort of 2 to 8 or 2 to 10 keV. And then for that flare study where I was showing you the two, I was just scrolling through and trying to find it again. Sorry, I did that in the wrong order. Let me share it and then make it full screen. This cut that we made here, so this is higher energies and lower energies, these are split around 4 keV. So it's 2 to 4 keV and then 4 to 10. So they're really just giving you a sense of the hardness ratio or the ratio between higher energy and lower energy photons. I hope that answers the question.
Excellent. Again, on the spectrum of Sagittarius star, towards the beginning of your talk, you showed the models that explain that spectrum. And the question asks, the model with green line kind of shows a double hump feature while the two other models don't. Could you please explain this?
Maybe could you or the question asker direct me a little bit more, because there may be too many different colors. This green?
Right. I believe it was, or in an earlier slide, maybe 4 or 5 even. Oh, no, not that early. 11.
Here.
I believe that's when that question came. So what makes the difference between spectra that show 2 humps versus the ones that don't?
Yeah, so I'm not exactly sure what this person was thinking about as humps, but maybe they mean this part of the green line and this part of the green
That's how
line.
I interpreted it. Yeah.
Yeah. Yeah. So these are different models that people have built to try to understand the accretion flow. And they're in particular in this example here using Yuan et al. Is one of our, our scientists who's worked really hard on these so-called radiatively inefficient accretion flows. So many of us carry in our mind, at least astrophysicists, this notion that as material falls in toward a gravitating body, it has a little bit of angular momentum, it tends to flatten into a disk, and that our accretion disk is a disky structure. If you have a fairly sparse disk, it turns out it's hard for it to actually emit enough radiation to actually flatten out into that nice tidy accretion disk. And instead it stays a little bit puffy, especially in the inner parts. So that's a very hand-waving way of describing what we call a radiatively inefficient accretion flow. And so these different models that you're seeing here are basically just showing you in quiescence, which is the green line here. You have that so-called quiescent radiative accretion flow, radiatively inefficient accretion flow, where you have most of the emission coming from something that's a little more disky, a little bit more of a kind of a disk-like spectrum, and then a little bit of an X-ray component in this model. I'm not sure I can do it off the top of my head from the Yuan et al. Model, but it's a little bit of upscattering to X-ray wavelengths, even when you have no flaring. And then there's an additional component along the lines of some of the arguments I tried to make today, probably from synchrotron self-Compton or from non-thermal synchrotron emission that get like an extra component, if you imagine drawing it in here, that gets added to the green spectrum during the flares. Hope that helps.
I believe there is also a Bremstrom component at those X-ray energy bands.
Yes.
Coming from the whole flow, and then the synchrotron self-Compton, like you were explaining.
Exactly. Yeah.
Okay, two last questions. One is pretty short. Has neutrino spectroscopy been employed in studying black hole properties?
Yeah, so neutrinos are really exciting. So I mentioned a little bit LIGO in a few of my questions at the beginning. So that's one type of multi-messenger astronomy, but neutrinos have been our companion other messenger for AGN and black hole, supermassive black hole studies for a long time. So we don't have a lot of spatial resolution for neutrino studies. So we do see neutrinos, what we think are sort of astrophysical population of neutrinos. They're spread all over the sky. Localizing them is tricky, but when we have done that successfully, I mean the royal we, really this is the IceCube collaboration and people that work with them, they have found maybe an interesting coincident gamma ray flare and neutrino emission from a blazar, which is affectionately now known as the Texas blazar, because TXS was the beginning of the phone number astrophysically. So the Texas blazar is one of our first examples of seeing something that we tie to an astrophysical messenger, gamma rays in this case, and a co-located and temporally co-located neutrino burst. And so that's very interesting. That was a big splashy result of a few years ago. There's also some very nice new work of a sort of an excess, a slight overdensity of neutrinos coming from a Seyfert galaxy that's much closer by. So we have a few tracers now trying to pull together neutrinos and astrophysical sources. People have thought for a long time that these neutrinos are astrophysical in their nature, but actually pinning them down to individual sources is surprisingly tricky. But yes, blazars are accreting supermassive black holes, just in case that's not vernacular that everybody knows. And we call them blazars because their jets are blazing right into our eyes. Their jets are angled toward our line of sight.
Okay, last question is on the sociology of the multi-wavelength campaigns. And the question is, what kind of issues arose when organizing a multi-wavelength mission such as this? How long did it take to convince all these telescopes?
Yeah, so I think that's a really great question. We spend a lot of time doing it. I would say the observatories are actually, as a rule, really excited. And we've gotten a lot of love back from the telescope allocation on these observatories. So I would say the difficulty, and this is a sociology about kind of all science, is that when you're striving to achieve or to understand an event that is serendipitous, you have to be very patient. And that means you might have many observing campaigns that go by and you have to report back to your observatory or to your telescope allocation committee and say, we got beautiful data, but there were no flares. Yeah, this year we got gorgeous data, but there were no flares. Or this year we got gorgeous data, but the ALMA data just has a huge gap right on top of the flare, right? And you have to sort of ask again and again until you finally can achieve the data sets that really start to disentangle what is a fairly complicated problem. And so that's, you're both really excited and thrilled when you get these data, and then you open up the data and then there's like some instrumental effect, or there's a gap, or there's, no flares, and so you have to just be brave and go back and ask your colleagues to come back to this science case again. I would say that is the hardest part. And so far we haven't been sent home without data. Really supportive, but it's hard. And we work really hard to try to coordinate them. Coordinating with the EHT is just an amazing jigsaw puzzle. But there's definitely a lot of will and a lot of enthusiasm that doesn't make it easy to make it all fit together though.
Well, thank you, Daryl. Thank you for the excellent talk and answering the questions. I believe we covered them. And just as a reminder, if you haven't done the feedback, the survey is on that survey link is on the chat. It will just take a minute of your time. We really appreciate any sort of feedback that you can provide. And our next speaker is going to be Sarah Isaun. You're welcome to register right now so you get reminders and you don't forget about it. And we always try to advertise it on Twitter and other channels as well. So we're looking forward to seeing you all in the next talks in the series. And thank you for attending. And thank you again, Daryl.
My pleasure. Thank you all for joining.